Good morning, everyone. Welcome to today's IvS seminar. Today we have Davey, who is a postdoc in Yoon's group. He did his master's and PhD at North Carolina State University and has joined us here. And I think he's going to talk about some of the work he did during his PhD. So I'll give the floor to Davey.
Can everyone hear me? Yeah, great. Okay. So today I'm going to be talking about quantifying Roche Lobe overflow in the formation of merging black hole binaries, which is a bit of a mouthful. So I'm going to start by breaking that down. Start with talking about what merging black hole binaries are. Binary black holes are simply two black holes in proximity, co-orbiting. They're particularly interesting as gravitational wave sources. So gravitational wave observations are currently really only restricted to the really strong gravitational wave emitters, which are these merger events between two black holes. In order for them to merge, they have to gravitationally in-spiral, which is a very slow process that can take hundreds of billions of years, and we don't really have time for that. So the ones that we're actually seeing with gravity wave observation have to already be really close to each other before they become a binary black hole. So how do you get a binary black hole? This is the most common formation pathway as we understand it currently, where you start with a binary star system. One turns into a black hole in relative isolation of interaction, and then the other is now close to a black hole sufficiently that it is going to likely interact before reaching its own black hole possibility. Now, at each of these steps, there's sort of divergent pathways where we could end up with, for example, instead of a black hole, we could end up with a neutron star or some other remnant. This supernova here could blast away enough of the other star that it can't form a black hole anymore. But if we are sort of working backwards from the idea of getting to a binary black hole, we expect most of them were previously this at some point. Now that is called a high mass X-ray binary. High mass, fairly self-explanatory, X-ray because of the X-ray accretion flowing onto that black hole. One other thing. Gravitational capture is another possibility that's currently being considered in the literature. That's the idea that a black hole, a rogue black hole, could enter a system that's already been developing on its own. And that's possible, but it's disfavored at the moment, so we're going to focus on this possibility as how binary black holes are primarily forming. So, when these two objects are so close to each other, and that's very important because, again, that in-spiral takes so long, they have to be really, really close before they become a binary black hole. And when they're so close to each other, the gravitationally bound region is limited by the one next to them. So I'm labeling these as donor and accretor for reasons that'll make sense in a second. And you can see labeled here the L1 point. I should use the pointer. The L1 point here is the point where gravity is directly balanced between them. So outside of this Roche lobe, any amount of material that flows out here is no longer bound to the donor and can flow freely elsewhere, which is called Roche Lobe overflow. And this is when the black hole gets close enough to this donor star that it starts donating mass that accretes onto the accretor. Now, this generally is described in one of two ways, and unfortunately, the literature here is a little bit qualitative so far because there's only so much analysis that has been able to be done on Roche Lobe overflow. And this is either stable or unstable. Stable means that as the matter flows out through this overflow, the star either keeps an equilibrium over a long period of time or actually has its Roche lobe expand, in which case it no longer overflows and sort of cuts itself off. Whereas in unstable overflow, the more material that flows out, the more the lobe shrinks, which means more material flows out, and the lobe continues to shrink. And this runaway process is thought to form common envelopes, and maybe common envelopes also form binary black holes, but stable mass transfer is definitely a possibility for forming binary black holes. So as we go forward, thinking about the stability of the system tells us a lot about whether or not it's likely to form a binary black hole. So now I've talked about Roche-Lobe overflow in the formation of merging black hole binaries. There's one other word from the title to cover: quantifying. Now, as I said before, is it not going? I don't know what that was about. As I said before, a lot of the research so far has been indirect or qualitative in analyzing Roche-Lobe overflow. So I'm going to be talking about it in terms of a few key parameters that we're going to constrain in relation to how much it's overflowing. So how much it's overflowing is this f, the radius of the donor divided by the radius of its Roche lobe. So if f is 2, that means the radius of the donor is twice as much as the radius of the Roche lobe. That would be ridiculous. That would mean something like 7/8 of the volume of the star is not inside its Roche lobe. So we're not actually going to get to a 2. But a 1 would mean that it's exactly at its Roche lobe, but not quite overflowing. So we're looking somewhere in that range of just above 1. I'm using eclipse radii, notably because it's hard to define a single radius for a non-spherical object distorted by this outflow, and an eclipse radius gives us something that can be used directly by observers. All right, so that's what I mean by quantifying Roche-Lobe overflow in the formation of merging black hole binaries. And this is relevant because black hole binaries are this sort of new frontier for gravity waves, but we don't really know where they're coming from. So if this is so important to this future of of gravity wave observation, then surely people have already been doing things on this. So the study of Roche-Lobe overflow started 50 years ago with models that were purely analytical and not directly tied to any simulations because it was the 70s. So notably, this is assuming the overflow is pretty close to exactly 1. So this is very barely overflowing. And they assumed a small overflow region, took an isothermal approximation, and a number of other approximations I won't get into. Suffice to say that it meant that angular momentum transport was basically neglected from the entire calculation. There have, of course, been more recent models. This by Marchant just a few years ago takes a 1D hydrostatic approach and still uses some of the same approximations. It uses an adiabatic flow instead of an isothermal. And has some consideration here for the angular momentum transport, being that it's a sonic flow at a specific angle of deflection, but it does assume that it's largely radial, purely radial here, which again influences how much angular momentum can be transported, but such assumptions need to be made in 1D. In observation, we have seen a few strong candidate systems. M33X7 is the one that I'm going to be talking about for my own research because it is our best candidate of a system that may, in our real-life future, become a binary black hole. This system has, very fortunately for us, an eclipse line of sight, which gives us a pretty good idea of what's going on there. We have a couple of different observations of it. There were observations in I think it was 2008, 2009, as well as ones in 2022 that differed significantly, but not because the light curve that they were seeing was different, but different analytical methods. So this is where the theory from the previous 2 slides comes in so important. The observation can't tell us directly a lot of the orbital mechanics. It can just tell us about the luminosity of these two objects, and the kind of separating the two objects even is a little bit muddled in observation. So determining things like the radius of the donor star is a little imprecise. The earlier earlier observations showed a overflow of around f.1.05, so overflowing a little bit more than just a 1.0, but not by much. And this is a 1.2, which is very high. I know that doesn't sound very high, but 20% bigger than the envelope, than the Roche Lobe, means a huge chunk of the envelope is just in free fall, falling into the black hole. So that's drastically different, but in terms of observational parameters, that difference in radius is pretty small. So then we turn to simulation. A lot of simulation in Roche Lobe overflow has been similarly limited because of intent to scale. So population synthesis methods let us look at a wide range of stars or systems and model how they might affect the evolution of an entire complex system like a galaxy or the universe by doing hundreds of thousands of simulations, all separate and isolated. In order to do hundreds of thousands of simulations, each one has to be fairly simple. Most of these have been done in 1D, which again doesn't fully capture the angular momentum, and has to rely on some of those 1D models made previously. So these can't tell us a whole lot more than the theory already did, but there are more complex models that have been done. Particularly the ideal way would be 3D hydrodynamics. This gets into the actual flow of system parameters and how those are interacting with each other across different length and mass scales. Here's a shot from a recent paper. I think this was 2021, and they had around 1 million grid zones, which is a huge grid to handle. And of course, that makes it computationally difficult. So in the computational difficulty of 3D hydrodynamics, not only does that mean there hasn't been a lot of work in this, but it also means that we can't cover the entire regime of what needs to be covered in one simulation. So oftentimes, our donor star is something on the order of an O star, or potentially a giant, and the other companion black hole would be smaller than the dot. So that means that we'd need grid zones small enough to resolve tens of kilometers, but also enough grid zones to span hundreds of times the radius of the sun, and evolve it over hundredths of a second for maybe 1 million years, which is just not possible. So most simulations have had to take some real limitations into account. So those limitations, along with approximations made in theory, have left some things fully unknown. Largely, this comes down to 3 things. The rate of the process, because almost all of these that I've discussed, whether it's in theory, in observational models, or in actual simulations, have a prescribed outflow stream where they just say, okay, if it's outflowing this much, what else happens? But that doesn't tell us how much it should be outflowing. And related to that, how much it's outflowing tells us how long it takes. So we don't know how long this process takes until we actually get into that as a free parameter. We then need to consider where is that flowing and where does it end up. So where is it flowing? The geometry of the system can tell us a lot about observational concerns as well as whether it's likely to end up in a binary black hole, because again, we need to have enough mass left in the big star that it can still be a black hole, but we need it to be close enough that they can actually merge within a Hubble time. So we need to be really precise in how these two objects are losing mass, but not too much mass, while also getting closer, but not so close that they merge before being a binary black hole. Then where this mass ends up, it's unclear what the total system mass should be at the end of these, because some amount of this is going to get shot out in the process. It's presumably at least a little bit messy. And how much angular momentum that carries out also tells us about that change in position and how close they're getting to each other, because they need to, of course, get rid of a lot of angular momentum to get close. So this geometry I'm going to break down pretty simply into focusing on the mass ratio, which is something that observational analysis can tell us pretty clearly, and the binary separation, which at least eclipsing can tell us pretty clearly. Not all observations can, but I'll leave that to the observing people. But the binary separation tells us a lot about the merger probability, because again, we need to get very close. The rate is mostly defined through this m dot L1, so how much grams per second is flowing out through this L1 tidal stream. And then this relates to this timescale. This characteristic timescale is just the change expressed fractionally with the current Roche-Lobe radius. So how is the Roche-Lobe radius changing over time? Which is defined by a lot of things, but as we'll get into, some of those parameters are more important than others. So for example, the m donor is going to be pretty similar to this m dot L1 because that mass outflowing is outflowing from the donor, and that's either going to end up leaving the system, so changing the total system mass, or piling onto the accretor, adding to the m accretor, depending on efficiency. I'm defining efficiency by 4 terms, just a little bit convoluted, but bear with me. So I'm looking at efficiency of both mass and angular momentum, because we need to consider both. And I'm looking at efficiency of just the L1 stream in isolation, and the efficiency of the total system, which also includes donor wind and other outflows. These two have not really been considered separately before, because generally when people are doing Roche-Lobe overflow simulations, they sort of block that from being able to happen in the model. So comparing both of those will be important there. Okay. So now I've talked to you about what I mean by quantifying Roche-Lobe overflow in the formation of merging black hole binaries, why it's important, what's already been done, and what needs to be done. So if these 3 things, the efficiency, geometry, and rate, are so important, and they haven't been done before in 50 years, how can we get at them? So we definitely need to do 3D hydrodynamics. There's just no shortcutting that in order to track angular momentum at all in any self-consistent way, we need to do 3D hydrodynamic grid. We need a non-uniform grid in order to be able to model those really small, fast things happening around the black hole, but also include the donor star in the same simulation. This needs to be scalable to a large number of processors because the resolution needed here is just not going to be able to run otherwise, at least not in a human lifetime. And we also need to go deeper into this than just a prescribed outflow stream. We need to actually simulate the flows that are producing that stream. So VH1 solves a lot of these problems. It has been used for wind Roche-Lobe overflow and some prescribed outflow Roche-Lobe overflow simulations before. So it can solve 3D hydro problems for us. But it hasn't been done before this project with any deep simulation of the donor star outflows feeding a self-consistent tidal stream. But before we get into that, the first issue with VH1 is we need to match that to a good grid. we need to be able to model a accretion disk, which requires circular symmetry in order to maintain that angular momentum. We also need to maintain the angular momentum of system objects flowing out in other ways, for example, from the donor or circular around the edge of the Roche lobe. So all of these require a lot of circular symmetry, and we also want to avoid the polar singularity here. So we're using a yin-yang grid, which takes sort of a tennis ball set of two half grids paired together. But you may have already caught on to this. This is not going to be enough because we need circular symmetry around the accretion disk and around the donor. So we need two grids. We need one that can handle the circular symmetry around this, one around here. And this also allows us to have a second grid that is much higher resolution and one grid that covers most of the area on a much lower resolution to save some computational time. So the accretor length scale does not go all the way down to 10 kilometers. We're not getting all the way down to the black hole, unfortunately. But it is getting down to a finer resolution than has been done before. And unfortunately, just as taking into account assumptions, we are sort of limited in how well we can model the final approach onto the black hole anyway, since that would require a solution to relativity, which VH1 doesn't currently supply. So we can go all the way out to the solar radii we need. We can go down to the hundredths of a second we need. And 100 days is impressive, but not anywhere near a million years. So hold that in your mind for a second, and we'll get back to that. It's another problem to solve. All right. The envelope solution. So we need that self-consistent envelope to produce those tidal outflows. And I'm starting with a spherically symmetric isolated star and then mapping that on to the aspherical contours of the Roche lobe. So I get this in isolation and then distort that onto the shape of a Roche lobe by its equipotentials. All right. That gives us this. So you can see here it is a Roche lobe down to an L1 point, and we're overflowing it by some amount here. I think this is 1.01. And I have kept this all constant within the accretor lobe to avoid an inverted density gradient, because mapping by equipotentials, this would give us an inverted density gradient. I'm also cutting it off at this radius of the accretor, and you'll see when I hit play, I've also cut out the accretion disk. So this is just looking at what this would look like for getting the tidal stream to generate. And obviously, interactions with the accretion disk are not pictured here, but will be in some pretty pictures I have for you in a second. But we are able to use VH1 with this grid solution to get a self-consistent tidal stream outflowing. All right, so that thing I told you set aside about 100 days being very different than a million years, let's talk about that now. So instead of doing any 100-day simulation, I started with two 50-day simulations that are exactly identical except for their overflow. So every other system parameter is exactly as described by the Ramachandran paper of M33X7. One overflows 1.01 and one is overflowing 1.1. And then just directly comparing, if we only change that, what does that change about the system? But that doesn't get anything, that gives a direct comparison to observation, but doesn't get anything at this full million-year evolution. So to address that, I did a series of 20 simulations, starting from the lowest overflow that my grid resolution could model, And then each time, taking the steady state end solution of that and doing a piecewise evolution, where we basically say, take this for 1% of its time scale. So calculate the time scale for that steady state. 1% of that time scale forward, if everything stayed the same as the steady state, where would it end up? Then we start the second simulation from where that would end up. So across 20 simulations, this evolved from barely overflowing to 1.17 and covered the entirety of the Roche Lobe phase. This covers, I'll get to the exact numbers in a second, but 600 and something thousand years and has less than 100 years remaining before the system collapses, at which point I cut it off. Doing this by 1% of the time scale lets this be a variable time resolution, so we capture all the fast things that are happening. When there's fast dynamical things, the time gaps get smaller and shorter, but when everything's staying pretty constant, it skips on pretty fast. Okay, so high overflow looks very visibly different than low overflow. Notably, this is pretty consistent with the early predictions of Lobe and Xu, the 1975 paper, which was looking at almost exactly 1.0 overflow, so very, very barely overflowing, and predicted you'd see a pretty steady column of uniform width that curves only as it really approaches the accretion disk. This is nothing like that. This is clearly a funnel of mass flowing as quickly as it can and crashing into each other as it does. And I want to highlight one other aspect of this picture. This little outflow here. This is the splash from the shock wave of the tidal flow striking into the disk. And as it strikes in, some amount splashes out. But the interesting thing that we found here, which was not analyzed in previous research, is that this amount that splashes out is almost exactly the same, even when we increase the amount that's splashing in by 100,000 times. That was very interesting. All right, so that amount splashing in is this line here, the L1 stream, which we also see up here. The disk inflow is also keeping pretty close to it. They're overlapping each other up there. So we can see that distinct difference, but the external amount, the amount flowing off of the grid, remains almost exactly the same. It increases by a factor of 2 across these two simulations, compared to 5 orders of magnitude. The accretion value is the messiest. That's because this is modeling from the very inner bound of our accretion disk, and that accretion disk has a lot of shock fronts interacting with each other. And so this is not only messy, but is going to always lag behind what is actually inputting into the accretion disk, because there's just not enough simulation time to steady those flows. All right, talking about rate, those 20 simulations were maybe a little bit misleading on how much time has passed, because almost all of the time elapsed in the first 2. The first 2 simulations, this one is in wind Roche Lobe overflow, which is when the actual envelope is contained within its Roche Lobe, but the atmosphere of the star is not. And so we get only the wind outflowing. And then simulation B here is in stable Roche Lobe overflow, which occurs over a very long time scale. Simulation C here is still mostly stable, but as you'll see in some of the graphics later, it's clear that after simulations A and B, we start to see increasingly unstable mass transfer. And I've categorized the remaining 17 all in one big clump here, because they only cover 15 kiloyears. Notably, and this is important because of the observation indicating maybe it's at 1.2, it's only going to be beyond 1.1 for about 100 years out of a million. So we don't expect anyone to actually get an observation of that. It would be very, very lucky for us to observationally happen to find one that's in that phase. All right. So here's that cutoff that I was talking about. This is the unstable mass transfer onset. And it's really distinctive when we talk about the timescale that after these first two, everything fits this curve pretty steadily. The same curve, inverted, is true here for how much mass is flowing in grams per second through that L1 point. So this mass flux was already increasing from wind Roche-Lobe overflow to stable, but then drastically changed behavior as it moved into unstable Roche-Lobe overflow. Now, the timescale is very interesting because this is an observational bias as well, that this tells us even if most systems that go through Roche-Lobe overflow end up being unstable, we're still going to mostly see stable ones just because they stick around longer. There's also an important factor here that mostly stable and unstable, as I defined them earlier, are seen as alternate pathways. Either you do one or the other. And we clearly see here stable followed by unstable. So even something that is unstable isn't immediately unstable and may be stable for the vast majority of the time and then unstable very briefly. All right, efficiency. So again, 4 different parameters for efficiency. I know that's a lot, bear with me. All right, wind Roche-Lobe overflow, which we only have 1 data point for here. This is consistent with prior models of wind Roche-Lobe overflow, including through VH1, indicating a mass capture efficiency by the accretor of around 3%. Previous models indicate anywhere between 2 and 5%, so that's very consistent. And virtually no angular momentum being captured by the secondary. Of course, also the tidal stream values are 0 here because there is no tidal stream, it's just the wind. In this stable Roche-Lobe overflow, we have one of these leaping up before the others. As we form this tidal stream, even very young tidal stream here in this first step of it, most of the mass that flows into that tidal stream ends up with the accretor. Some of it, about 1/3, ends up falling out of the system, but 2/3 ends up being conserved in this interaction. Still not a lot of angular momentum happening, and this tidal stream is still being outweighed by the wind, so the binary system values haven't changed much because the wind is still the dominant factor there. But as we get into unstable, we see that unstable Roche-Lobe overflow is predominantly 100% efficient, meaning that, as we saw with that previous slide, even when we increase the amount flowing through the L1 point by 100,000 times, the amount outflowing barely changes. There are 2 features here I want to talk about, and they're unfortunately due to simulation limitations. This one, particularly affecting the tidal stream values, you see almost no change to the binary system values, is from the limited time of the 3 days of simulation for each one, which was something I wanted to keep constant across these simulations, but that was based on looking at this first one. And so I didn't recognize that as I would ramp up into unstable Roche-Lobe overflow, 3 days would no longer be enough time to circularize the accretion disk. So what's happening here is, though no mass is leaving the system, mass is splashing out in big arcs around this accretion disk and not being treated in quite as consistently. So as of this cyan line, I modified my code to now inherit the disk of the previous simulation. So now, instead of only having 3 days to initialize the disk, it can take one that's already most of the way there and add 3 more days to it, and add 3 more days to it, and add 3 more days to it. So this immediately fixed that problem. It did lead to a secondary problem, which again, limit of how I was handling this, because of not being able to go all the way into the black hole. I'm modeling what's flowing into the accretion disk with a spherical surface around the accretion disk. And I thought I had done that fairly conservatively, but my estimate was actually a little off for these high overflows that go past that 1.1 simulation that I'd done previously, in which the accretion disk ended up being bigger than the sampling area. And so this dips here because a large percentage of that mass is being deposited in part of the accretion disk outside of where I'm sampling it. And so that's just being miscounted because it's outside of that zone. But once it fills in that accretion disk, now that it's able to inherit it, it can fill that in, and then that stays at constant size beyond that, and you can see it returns to this 100% with that wider disk. Another notable thing about the geometry is in these feeding flows in the envelope that are generating this tidal stream, this produced such a strong outflow that we actually get complete turnover in a couple places here, there. I think there's a fourth one, but anyway. So we get several complete turnovers, which is traditionally expected not to happen in a radiative envelope. And here is still quite localized. We see nothing like it throughout the rest, only basically directly underneath the tidal stream and stuff that is flowing upward, and the countervailing stream backfilling the stuff that's flowing upward. But that does suggest that there could be a dynamo effect occurring there with how powerful these flows are that may be just not taken into account in 1D models because they can't track that. As it flows out of the star, the 1975 paper suggested, sort of as a simple approximation, that it would leave as a transonic value, meaning that it's flowing out at the speed of sound at the L1 point. As you can see here, at the L1 point, it's almost exactly at Mach 1, which is a solid confirmation of that. We also see an interesting change in disk structure that formed sort of emergently. And asterisk, I don't know why this is happening with the disk. I have verified that it's not due to simulation. This seems to be a physical thing that's happening. Not sure why, but there are disk gaps that form. So here, it's higher density, lower, and then higher again. And then particularly pronounced over here, it even gets down to almost the low density of this light blue out here in a strip before getting higher density again, which does not seem to correspond to any harmonic values, but not sure what's going on there. All right. Talking about our key parameters in geometry, we have Q and D, the binary separation, and the mass ratio, both of which follow an exponential with the overflow parameter. Here you can see the binary separation across these simulations has gone down significantly from 35 to 31 solar radii. The mass ratio has gone down a lot less, from 3.3 to still around 3. So this suggests that maybe if I let these simulations go on ad infinitum to fill in that remaining 100 years, we'd see the binary separation cutoff first. So this would be something that maybe merges before becoming black holes, a second black hole rather. But it's hard to say because I'm not modeling the evolutionary response of losing that outer envelope, which could lead to a supernova changing all of the dynamics. So what did we find? We found that wind Roche overflow was consistent with the efficiency previously predicted. Stable Roche overflow was greater than 50% efficient, and unstable Roche overflow was 100% efficient. Broadly speaking, most previous models roughly assumed a 50% efficiency, just as a crude first-order approximation. And it seems that it's more efficient than that, and particularly unstable Roche-Lobe overflow may be taken as fully conservative in future models. The model of Lubo and Shu, as one might expect, for assuming overflow of 1.0 almost exactly, doesn't really hold up at high overflow, but the method of Marchant is broadly applicable to a wide variety of overflow parameters. We found two novel prescriptions for system geometry and the rate of flow as they relate to the overflow parameter. And also found that high Roche-Lobe overflow observations are very unlikely given how brief the process is, which was not something that could be commented on when the timescale of the process was not known. All right, thank you so much.
Thank you very much, Davey, for this really interesting talk. Are there questions?
Thank you. It was a really nice talk, but very theory heavy. So I didn't understand everything, but the main message. But I was wondering about, in your simulations, you said that you evolve over the entire mass transfer phase later. And I was wondering, how do you know how much your star will expand? Because this depends on many physical structure parameters.
Yes. Yeah, good question. So sorry, 1 second. In these first two phases, there is a potential of a feedback evolutionary process that changes the diameter of the star. However, given the type of stars, this is a class O star, and the existing literature suggests that it only responds on timescales of interaction greater than 1 million years. So there's a potential that it interacts on hundreds of thousands of years. But after that point, we can be pretty confident it's not able to respond in any significant way on the timescale of the unstable overflow. There is, of course, an issue with that as well, that as I initialize this envelope back to the same radius each time, I am actually overestimating how long that will take, because I am initializing it assuming that it has had time to reestablish some amount of equilibrium, which it will not beyond that point. And so it'd actually be denser, more higher entropy outflows, and actually lead to an even shorter timescale in those later ones. Does that answer your question? Yeah. Okay.
Hey, Davey. Thanks for this talk. I have a question for the observational point of view. I didn't see the comparison maybe to the observations of, what was it called?
M33X7, yeah. So the star I'm using here, this is M33X7, the companion black hole. The notable observational parameter I wanted to compare to was, while the system's mass ratio is fairly well defined, and the binary separation is well defined because of its eclipsing sightline, the radius of the donor was the big unknown. And so in comparing this low overflow case, this is more consistent with the simulation, or the observations of it in like 2008. And this is more similar to what Ramachandran saw in 2021. This seems highly unlikely, especially at 1.2, because again, we would have to be very lucky to see it on that time scale. And if it was on that time scale, we would see a significant difference in light curve between 2007 and 2021 because of how quickly it would be evolving at that point. That if it was at 1.2 overflow, it would have less than 50 years to live.
Okay, cool. Can I ask another question as well?
Yeah.
So you have these efficiency parameters.
Mm-hmm.
What you were basically saying in that plot is that they will all be 1, basically.
In
the unstable phase.
In the unstable phase, yeah.
Okay.
Yeah, which particularly as it gets into unstable, the difference between the binary system and tidal stream values is negligible because the binary system is almost exclusively the interaction of the tidal stream is almost all of the outflow that's happening, heavily outweighing the wind by multiple orders of magnitude. But the advantage of tracking both of these was being able to identify when these features were erroneous. And so that allowed us to identify that does seem to be a conservative process.
Hello, thank
Hi.
you. Interesting subject and interesting talk. I was wondering if anyone ever tried to model these things with a particle-based code, because then maybe some problems might be easier, like the resolution follows density, so around your black hole you would also get higher resolution, but maybe there's things I don't think about that make it more difficult. But do you know if it's been tried?
Yeah, so you're talking about SPH, smooth particle hydrodynamics codes, which have also been done in this area, and that has some advantages and some disadvantages. Particularly, smooth particle hydrodynamics has the ability to track things that you know are flowing out from a particular vector, such as here, and where those end up. I've sort of done a particle trace simulation through that. But the downside of smooth particle hydrodynamics in this is while it works very well with a wide range of length scales, so things can be, the same particle can be tracked on a very smooth arc or a very fast turn without much computational overhead. Those particles are of a set density or mass, and the density regimes here are very different. So being able to track the wind contribution, which could be 10 orders of magnitude less than what's going on in the disk, is a little bit difficult for SPH to handle. There are oil on water simulations where they model 2 or 3 different densities of particles to track sort of different density scales. But as you can see here, the accretion disk dynamics can lead to drastically different from one simulation to the next. So I'd have to tweak which particles I'm using in the piecewise evolution. So it can't quite do the piecewise evolution the same way.
Okay, thank you.
Okay, so thank you for the talk. So you mentioned that you need to map a 1D structure profile to 3D Roche potential for your simulation. Can you say a little bit more about this?
Yeah.
Yeah.
So let me go back to it. Here we go. So the 1D profile is fairly simple, not including the iron bump that some of the simulations here add in. We have this power law temperature as well as this curve to the density. These are then just taken in terms of radius in the 1D model. And then that radius is equated to a gravitational potential difference from one radius to another. And those are mapped onto these contours for the gravitational potential of the system. So it's considering this whole line here as if it's at the same radius. And this allows a fairly simple way to initialize without having the kinds of backflows that you'd get starting from a spherical solution and then slowly perturbing it into these equipotentials, but allows the kind of radiatively dominated envelope to form. Does that answer your question?
No, thank you.
Hey David, really nice talk. So I was wondering about the resolution as well. So in the beginning you talked about like the high resolution part and the low resolution part. So assume you're using like two fixed high low resolution, right? So so my question is like would you like is it possible to like do with some sort of like a adaptive refinement kind of, because maybe there will be like, as for example, you have different density points, right? So probably that's, or it's difficult to be done in this.
Yeah, so two things to say about that. Let me go into one where you can see it a little bit clearer. Here we go. So it's not quite two resolutions. The two grids each have scalable resolution with radii. So the zones further out here than here are going to be larger in order to maintain roughly cubic shape with the increased angular size as they go out. And so the same thing's happening here. So these innermost grid zones are, I think, a fifth, something like that, about an order of magnitude smaller than the ones out here at the outside of the accretion disk. But there is still the issue that we're not going all the way into the black hole. And so an adaptive grid might be able to help with that. We are running into an issue of sort of the maximum resolution that we could feasibly achieve. This is a grid of, so it's yin-yang, so each one has two grids, and there's two yin-yangs. So you have four grids, each of on the order of hundreds by tens. So it's 512 by 256 by 96 times 2 times 2, which is, I think, like 100 million grid zones. So adding in an adaptive grid may be too much computational load, but could be very helpful. And particularly, once this grid has sort of reached a steady state, we can kind of just ignore that whole grid and focus on the much slower evolution of the disk. And so that's where maybe taking this as boundary conditions on a grid solution for the disk might be where adaptive mesh could be more helpful.
Okay, thank you. Also, I was wondering if I can ask one more. So, so about so the evolution of the star itself, right? So I was wondering, like, you are reverting back the radius every time, or like, is it possible, like, if you run, say, some sort of 1D stellar evolution code and then revert back the radius to that rather than to the, or yeah?
Yeah, absolutely. So the eclipse radius is being held constant here, and a future improvement that I have in mind for this would be to, like you said, compare with a, say, MESA, some sort of evolutionary model across that 250,000 years, and see what sort of response would happen in the radius of the star, because that could be really substantial. And I think I may have undersold that earlier, that in this point, when the Roche timescale is very slow, it could be that the thermal response of the star is enough to just slowly expand that Roche lobe and keep it there forever. Yeah. If I properly account for that evolution, it may be that we just stay in that forever, or it might be just slightly prolonging or shortening it before a big dip. hard to
Yeah.
say until we actually get into that. But yeah, definitely something I'd like to do.
Okay, thank you. Yeah.
Thank you for the very nice talk. You mentioned that these two tidal streams for the two different overfilling factors are nearly constant. Can you comment on why that might be?
You're talking about the outflow here?
Yeah.
Yes, okay. So this is really interesting because what I anticipated was, sort of my hypothesis going into this, was that the shock front, as it collides onto the accretion disk, would scale up how much is outflowing. I would expect that that outflow would be proportional and that we'd stay at a fairly uniform efficiency of maybe 50, maybe 70, hard to say. But seeing that it didn't evolve at all was very fascinating, that this only increased by about an order of by an order of 2, across such a drastic change in tidal stream seems to come down to how dense the accretion disk becomes. Let me just compare some orders of magnitude here. This being e to the negative 10, this being e to the negative 6. So that's gone up by 4 orders of magnitude, but the disk has gone up from e to the negative 7 to e to the negative 3, so 4 orders of magnitude. And either way, it is substantially more dense than the material flowing onto it. So it's sort of keeping up with minimizing that shock, being able to absorb that shock just by how much mass needs to be moved. And so that means that it can be sort of corrected for by the noisy other shock waves constantly hitting off of each other in that accretion disk. But another factor that is not being included here is the X-ray feedback of that final accretion onto the black hole. So like I said, we can't go all the way into the black hole with this model. If we did, we'd get X-ray radiation that pushes back out on that disk and would certainly increase the outflow by some amount. It's unclear how much, especially with such a dense disk as we get in the high overflow, but that would increase potentially more in scaling. But just pure hydrodynamics, I think that just comes down to the disk being able to absorb that shock front into a bunch of its other noisy shocks.
Cool, thank you.
Thanks. I think we have time for maybe one more question. Yeah? Or Frank?
Hi, yeah. Nice talk, Davey. I'm curious, because you mentioned you don't go all the way to the black hole, which is understandable, it's very difficult. But from what I also understand, it's very difficult to have 100% accretion rate from an accretion disk onto an object. So the efficiencies you mentioned right now, they're like 100%, nearly almost all matter goes into the accretion disk. But I feel like a lot of it from the disk would still be lost before it actually reaches the object. And how do you have an estimate of how significant this could be and how much effect this would have on the other outcomes of your orbits and such?
Yeah, so particularly it goes into what I was just saying about the X-ray feedback would affect that accretion efficiency onto that final black hole. But I want to modify that in the discussion by pointing out that the accretion disk is still going to be there when it leaves Roche Lobe overflow phase. So we don't have to fully clear the accretion disk in this phase, and then most likely the donor star will evolve either into a merger, into a common envelope, or into a supernova, into its own remnant before most of that mass that gets deposited into the accretion disk ends up anywhere. So it may deposit a bunch of mass that does eventually leave the system, but in observations of this phase, it doesn't leave the system during the Roche Lobe overflow phase. So that might look at what is the efficiency of that accretion disk clearing itself as the two black holes sort of in spiral into that final merger. And that is going to have a lot of complexifying factors. For example, we're going to be right in front of a supernova of the other star, and that could blast off a bunch of this. That could just immediately remove a chunk of the accretion disk, or change a lot of the dynamics of the accretion disk as it deposits all of that outflowing velocity. So there is definitely a sort of limitation here that I'm not considering that final approach onto the black hole and that final accretion. But the flow of angular momentum in the accretion disk is being handled fairly self-consistently enough that the stuff down here is maybe a little bit different than we might genuinely see because of interactions with the black hole and X-ray feedback, but the stuff out here is probably quite consistent with what we would see. And this is where those final outflows out of the system would be occurring. So I expect that would have an effect. I don't know if it would be significant effect to move that 100% by a significant percentage down.
Okay, I think as we're past the hour, we can thank Davy again. And see you all next week.
Should we start?